Let's solve USACO Silver Problem 1 2017 cow dance show. So we're given a sample input where the first line represents the number of cows, n, and Tmax, max stage time. And then for the next n lines, we have dances. So what does a sample input mean, or what is the problem asking about? Well, let's imagine a stage where we have n number of cows that wants to dance on the stage. However, we have some limits to the stage. Within our contract, we only have Tmax, which is represented as the max stage time our cows can dance on the stage for. Now, the bigger the stage, the less time we take up on stage. Therefore, if we have all 5 cows dancing at the same time, it will only take a time of 8 units of time on stage. However, we are trying to figure out the smallest possible stage size within the contract limit. The contract limit is our Tmax, meaning we want to reduce the size of the stage, be more efficient about it. Maybe it takes a size of 4 to accommodate all the cows within a contract limit. So let's see how that looks like. So let's say I have a stage size of 1. So let me just erase these 3 cows. This means we can only dance 1 cow at a time. So let's input our stage size that can be represented as a list or an array. And let's start off with the first cow, which is 4. So 4, and the time elapsed is 0. After that cow is done, we fill in the gap with 7, the next cow, and the time elapsed was the previous number, which is 4. And then we fill it in with the next cow. Now we grab 7 plus 4, which is equal to 11. Now, this is where there's a problem. We already exceeded the contract limit of Tmax. That means automatically this fails. So let's try a different stage size. Let's say 3. So if the stage size is 3, we start with the first 3 cows in the dances array. Where's 4, 7, 8. So 0 time has elapsed. So next, we look for the smallest dance time, which would be 4, and elapse that time. So we essentially subtract 4 through everything, and we'll get this array 0, 3, 4. So time elapsed was 4. However, we need to fill in that gap with the next cow, which is going to be 6. Then we'll do this again by elapsing by the minimum dance time, which is going to be 3 this time. So we subtract 3 against everything, then add that 3 to our time elapsed. And so far we have not exceeded our contract limit. So let's go ahead and fill in this spot with the next cow, which is 4. Now, we have no cows left to fill in, so we're just going to look for the max cow time and elapse that time. So we essentially subtract by 4. We run down the remaining cows, which is 0, 0, 0. So now that we elapse this, we add a 4 to our 7, which will be 11. Now, again, this was not within the time contract limit, which was 8. It exceeded it, so this is a false. So from 1 through 3, we see it is false. So what about stage size 4? So stage size 4 starts with 4, 7, 8, and 6. So we elapse by the minimum time, which is going to be 4 again. Then we fill in that spot with the next cow, which is going to be 4 this time. Now that we have 0 remaining cows to dance on stage, we run down the clock by the maximum. There's 2 maximums of the number 4. So we elapse the time by 4. So 4 plus 4 is 8. And then after those elapsed 4 seconds, there's 0 cows remaining on stage. This was within our max stage time of 8, which means it was within contract limit. So now that we have solved stage size at 4, let's look at stage size 5. So anything past stage size 4 is going to work because we're increasing the size of the stage, therefore reducing our time limit on stage. And as we can see, stage size 5 is the same length as the number of cows that are going to dance. Therefore, our biggest answer should always be n, where we have all the cows dancing at the same time. And the amount of time that's going to take is the cow that dances the longest, which is an 8. So the time elapsed is going to be 8 in this situation. Now, most people's approach is to start from 1 and then keep incrementing until we hit a within contract limit solution, so linearly. However, if you notice, there's a pattern where there's a set amount of answers that don't hit a contract limit, and then after that, there's a set of answers, multiple answers, where we're within the contract limit. Since we are trying to search for the smallest possible stage size within contract limit, we can use binary search to find this convergence between a false contract limit and a true contract limit. And that takes significantly less time to search for. It reduces our time complexity for search from O of n to O of log n. So that's the first step to solving this in terms of programming. Now let's talk about the next step. So earlier in this graph, I discussed how we find the minimum dance time, then elapse or subtract the entire stage time, then fill in that open spot with the next cal. So that's going to take O of n time and then an O of 1 time to fill in. And that does it repeatedly until we free up the stage. Now, I'd like to call this just the normal binary search on array approach, or a brute force approach with just binary search. What we could do is instead use a heap, along with adding time on top of the root of the heap, then adjusting the order properly continuously. So let's talk about how this heap priority queue approach is going to look like. In our first case, we have k is equal to 1, where we just fill in with 4. And instead of subtracting every single number in our stage array, we add the minimum dance time to the next dance time. So we're going to add 4 plus 7. So 4 plus 7 is equal to 11. And just to mention, heap priority queues, specifically a mean heap, makes it easy to access the minimum dance time in an array or in the queue. So if you realize there's a pattern here, you can already see what the time elapse is going to look like after our time elapse has elapsed by 4. This 11 indicates the time elapse, the maximum time elapse in this array. So this is automatically going to be a false, just like before. And just for the sake of completion, let's just add 11 plus the next cal time, which is 8, plus 11 is going to equal 19. However, we could just stop here. Let's continue with stage size k equals 3. Now we have 4, 7, 8. So now this is where our heap or priority queue take into effect. We heapify the list or the subarray of dances, which is 4, 7, 8. It's already in order, so we keep it as 4, 7, 8. Now, 4 is in our root, since it's a min heap or a min priority queue, and we just add the next cal time limit, which is 6. So 4 plus 6 is 10, 7, 8. I essentially pushed in a new value, so I need to readjust the heap priority queue order property. So we change the positions of 10 and 7. We shift 10 at the end using a method such as heap push and heap pop. Now, only a unit of 4 time has elapsed. So let's continue. We find the minimum dance time in this stage array, and we add the next cal dance time, which is going to be 4 up here. So 7 plus 4 is equal to 11, and then 8, and then 10. Using heap pop and heap push, this will reorder the heap or priority queue, where we have 8, 10, and 11. Now we're out of cals, and we just look for the max dance time and elapse that time, which is 11. And you see that the max dance time at the end of this heapify process will always return the total time elapsed on stage. Now let's continue to do this at stage size 4, where we have 4, 7, 8, 6. Now we need to heapify this or build the priority queue. We can easily access the minimum number in this min priority queue with 4, and we add the next cal dance time, which is going to be 4, and that's going to be 8, 6, 7, 8. Then our built-in methods are going to reorder the heap priority queue. So 8 gets pushed back into here. Now we have 2 values that are 8. However, we only really care about 1, even if they're equal, and elapse that maximum dance time limit inside of this queue. And that's going to be 8, just like before. This saves a bunch of time. We're not using a O of n time complexity like here when adjusting the stage size or stage arrays. We're quickly reordering the property, sometimes in O of log n, and this is the benefits of using a heap priority queue over a normal array. And for 4, 7, 8, 6, 4, we'll just heapify this. So it'll be 4, 4, 6, 7, 8. We just grab the max dance time, which is 8, and then elapse that time. And this is the heap priority queue approach. It is faster than this approach here. And now that I've discussed how it works, let's write step by step how to pop and push into this queue quickly. Now first, the stage has to be a subarray of dances from 0 to k, the size of k. So let's say it's here, 0 to 3 subarray of dances. Next, we need to heapify or build heap. I like to say heapify this stage. Next, we continuously elapse heap or pop shortest dance time and add next cal to dance spot. So what does that look like? So for index in range from the starting of k all the way to the end, we grab min dance time from the root, and I'm going to do two things at once. I'm going to pop the heap since we're not going to need it anymore. So pop the root, save that number, then we push the min dance time plus the dances of the current index. This index represents the index inside of dances. Now, in programming languages like C++ and Java, it is a good idea to record your maximum number each time. And we're going to call this max elapsed time. And we're constantly comparing the new values that we're pushing into the heap. So values like here, where we had 10 and 11, we want to keep track of the biggest number. So we can go ahead and just return that at the end. And then compare it to tmax to check if it is within a contract. So let's do this example of stage size 3, where we have 4, 7, 8. Now, we quickly find out the minimum dance time is 4, which is our root. So we then pop it. So pop the 4, but we save that value. Then compute the value we're going to push into the heap, which is min dance time plus the current index of dances. So the current index where we're at is actually 6. We started from 6. So that's the element we want to add into. So that's going to be 10. This equals 10 right here. So when we pop the heap, we reordered the property where it's 7, then 8, and then we pushed in a value of 10, which goes right here. We also save this value in max elapsed time, since it's our new max. Now we'll continue doing this where we're at index n, element 4. So this changes to a 4, and the minimum dance time is actually 7. Now 7 plus 4 is equal to 11. So we popped 7, and we need to reorder this where 8 goes up here, 10 goes here, and then 11 goes here. Now, our max elapsed time has also been saved to 11 yet again. So we go ahead and do this condition statement where if max elapsed time is less than or equal to tmax, it is true, else it is false. And we continuously do this on top of multiple binary search problems until we find this convergence of false and true. This is what we want to return. The smallest possible stage size within contract limit. And that concludes the most efficient way to solve this problem. So let's start solving the USACO Silver Problem 1 2017 Cow Dance Show in Python. So we have our sample input cowdance.in, where the first line indicates n, number of cows, and 8, which is the time we're allowed to use a stage that we're going to dance on for the cows. So tmax. So earlier I said the most efficient way to do this is by using a heap. So we're going to start off by importing heapq for Python and then opening our input file. Then reading the input file and recording that first line where n is equal to num of cows Tmax is equal max time for all cows to dance on stage. So that's the contract time limit. We can map that first line into two integers, n and tmax, by splitting the line into two integers. Now for the next n lines, read each cow's dance time. The way we can do that quickly in one line is by creating a dances array. And what I mean for the next n lines is lines 2, 3, 4, 5, 6 here. So this is how long cow number 1 wants to dance for, cow number 2 wants to dance for, cow 3, and cow 4, and cow 5. And we need to go ahead and store that information as integers. So we're reading each line in range of n. Now, earlier I said we have a list of problems where our answer can be at the very minimum 1, at the maximum the size of our cows. So we want to figure out or search for the smallest possible stage size within contract limit, and we can use that we can search that using binary search. So I'm going to say binary search for smallest possible stage size within contract limit tmax. So this can be our left pointer and our right pointer, our low and high. So 1 and end. And I'm going to say while low is less than high, we're going to make the binary search algorithm. So we calculate mid by grabbing low plus high divided by 2 and rounding down. Now I can make this really simple for people to understand. We're going to have two if-else statements, and that's really it. So if not within contract, and by the way, we're going to make this into a method. We're going to say k is equal to mid. We're feeding in mid into our method as k. So if it's not within contract, that means we need to increase the stage size to reduce time on stage and be within contract time limit. So we can do that by grabbing low and then setting at mid and then skipping over mid by 1. Else, we can record high to mid. This means this is within contract, this else statement. We want to record our high. And at the end of that, we can write searched item into output file. And it will converge where there's a false and a true. And in this case, I'm going to say high because I'm constantly updating high where there is a solution. And then I'm going to print that out to our output file. Now, I still need to create my within contract method. So k represents the size of the stage to support n amount of cows dancing. And our input is going to be k, which represents the size of stage. And remember, k at most is n and at least is 1. So stage is going to grab a subarray of 0 through k. However, we could just say colon k in Python. And I'm going to use dances here. So it's grabbing this value. Then there's two approaches to doing this. Now I'm going to talk about the less efficient approach where we constantly decrement the minimum distance. So that would be something like this d index less than n. And then there's another for loop inside of this where we decrement the minimum dance time. This is really inefficient. So let's talk about how to do the heap approach. So we grab stage already. Now we need to heapify it. Now this is a min heap. That means our minimum dance time is always at the root. It's always at the first element of the heap priority queue. Because of that, we can elapse shortest dance time and add next cow dance time by pushing. So let's start off by iterating through stage. So for index in range k through n, since we already got it 0 through k here, and then we can find the minimum dance by just popping the root, then pushing that same minimum dance time plus our new cow dance time. So let's say there's an array stage of 4, 7, 8. It would pop 4, save that 4, and then add a 6 for the next cow dance time. So 4 plus 6 is 10. So now we have 10, 7, 8. Pop the smallest value, which would be a 7, save that number, and add it to the next cow dance time. 7 plus 4 is equal to 11. And then we can quickly find out what is the total elapsed time for the stage by just returning the max stage dance time that we've recorded using heaps, and then comparing it to tmax. This is extremely fast. This is using binary search, then heap push and heap pop methods within the range of n, and that equates to a total time complexity of n times log n. And our memory complexity is just O of n, where it's dances, and this is the most efficient approach to solving this problem in Python. So let's go ahead and run it. And we got an error, so let's go ahead and fix that error where I didn't close this int parentheses, and then run this one more time. And I got another error, so I need to separate caldance.out with w. These are two separate arguments. And then compile, run it, we get 4. So this is our solution with our time and memory complexity. This is the finished version and the most efficient approach to this problem. We were able to find the smallest possible stage size within contract limit. So now we're going to test out our Python code on the website. So we're going to select Python 3.6.9, then choose our file. I called mine test.py. We submit. And we passed all our solutions. So that concludes the Python solution. So let's try to solve this problem from USACO 2017 January Contest Silver Problem 1 Cow Dance Show. So earlier I talked about how we want to use a binary search with the heap priority queue approach. And the way we can do that is first by opening up our input file. And just for the sake of this problem, I'm going to go ahead and include certain libraries one by one instead of bits/stdc c++.h. So we want to start off with fstream, also iostream. We can open our input file caldance.in by using ifstream, fin, caldance.in. Now, great. Now let's talk about what the problem is asking for. The problem is asking for how many cows we can put on a stage and dance within a time limit, a specific contract time limit. And the first line represents n, number of cows, and t max, max stage time, contract limit. So that first integer is n, and that second integer is t max. And I actually want to save these variables for later. I want to make them as global values. Global integers, so I could use in my methods if I decide to use them again. So now for the next n lines, read in cow dance times. So these next n lines represents how long a cow wants to dance on the stage, and I want to gather that information with the for loop. I use the integer ln to represent each line. Then we want to grab that input and append it to a vector using pushback t. Now I haven't created the dances array, so let's go ahead and do that up here as a global vector integer or integer vector. We also need to include the vector library. Now that we have gotten our input file, our inputs, let's go ahead and close that. Now earlier I told you that we can binary search for the smallest possible stage size within a contract time limit. We want to converge where there's a false right next to a true, basically. We can represent k like this, where it is at least 1 and at most n. Therefore, our integers variables are going to start with low is equal to 1, high is equal to n. It's within this range that we're searching with binary search. And we could use a while loop to do the binary search algorithm. So let's calculate mid in every iteration by grabbing the low number, then adding half the distance by using high minus low divided by 2. So it's realistically two parts, low plus half distance. So we don't run into any errors where the mid integer is too big for the int data type. Now, I can really simplify this binary search by saying, if not within contract, specifically the mid value, that's going to be represented as k in a method we're going to use soon, we go ahead and increase low. What low is essentially doing here is increase stage size to reduce time on stage and be within contract limit. Therefore, else is going to do almost the opposite, where high is equal to mid. And we will converge to an answer where we write the smallest possible stage size to output file using high. Then we can go ahead and close our output file. Now the tricky part is making this within contract function. So let's go ahead and create this right up here. So based off this if condition, we need to make a function that returns a boolean and is called within contract. And our input is going to be k. it is this k we're trying to find out, the size of the stage. And as earlier, I said we're going to use a heap/priority queue to cut down time. So we need a heapify first k cows. We're going to use a priority queue where we have integers and it is a min heap. I am essentially slicing in this parentheses here, where we grab dances 0th index to dances 0th index plus k. And we need to include the queue library. Now that we heapified the first k rows, we essentially elapse shortest dance time by popping the root to open a dance spot and add next cal time on stage by pushing the popped root and adding current index. Now that's really long, and I'm gonna go ahead and make this a little bigger and start our for loop. So we're starting for int index is equal to k. So we're starting where k left off here and stopping at end. We're incrementing by 1 each time. We're iterating through the dances vector, then first finding the min dance by using stage.top and saving that min dance value. It'll come in handy later. Then we'll go ahead and pop the root, then push that popped root plus the current element of dances we're looking at. As this continues pushing, we are pre-calculating the total amount of time we're going to use the stage by saving the max dance time. So we are going to go ahead and return max dance, then compare it to tmax, and that will return a true or false. Now, there really isn't a max function for a priority queue when we're using a min heap, so we need to create that. We can constantly update a value named max dance, and I'm going to go ahead and put this at the lower limit, so we definitely update max dance. We're going to use the limits library. So it's an integer. We initialize it with the minimum value, and then we go ahead and update it each time we push a new value. It's going to be max dance. We go to max, compare max previous dance to this same pushed value. Then we can easily figure out what max dance is later on. So let's go ahead and run our code. We see we got an error at 37. I forgot to close this with time. Same here. Let's go ahead and run it one more time. And we got 4. That is what we were looking for this sample input. So this is our final solution where we use a binary search on heap priority queue. We have a couple global variables and we have a function named within contract to easily read the binary search algorithm below. We have a couple libraries and I want to talk about the time and memory complexity. So the time complexity, we're using binary search, which is log n, and then we're using heaps where it's O of n, and then constantly using pop and push methods that use O of log n. Now that total time complexity results to n times log n, or n log n. And the memory complexity is just the size of dance's array, which is just n. So that completes our solution. Now we're going to go ahead and run our solution on the site. So let's select C++17, choose the file. I named it test.c++, then we're submitting. And we passed all our test cases. That concludes the problem for C++. So let's solve USACO's 2017 January contest Silver Problem 1 Cow Dance Show in Java. Now earlier I talked about using a binary search on with priority queue approach on searching for the smallest possible stage size within a contract time limit for the cows to dance on a stage. Now, the way we can do this in Java is by first opening our input file. And our file name is called cowdance.input for our input file. Then our first line is n, which represents number of cows, and tmax, max stage time or contract time limit. Now, I want to make these variables global or instance variables. So I'm going to put this right outside of our main method. So this makes these values accessible to all methods, and it will come into use later. Now, for the next n lines, we read each cow's dance time. And then we're going to add it to a list that is dynamic named dances. So we constantly append new values from the input file on each line. And I want to make this accessible to all methods. Again, it is a list data type. We're naming it dances. Now that we gathered all our data, we can go ahead and start solving the problem. So the problem is, yet again, I'm going to re-emphasize, is we're searching for the smallest possible stage size within a contract time limit. We want all our cows to dance this amount of time, where cow 1 wants to dance for a unit 4 times and so on. That is why we're using a list named dances. Now, we are trying to find out what the size of k is going to be, and we know that the smallest possible size the stage can be is 1 to accommodate 1 cow, and n to accommodate all the cows in our dances list. That means there's a lower and upper bound where we can represent as low and high. So we can binary search for smallest possible stage size within contract time limit, where we use an integer value named low, start at 1, and high ends at end. And we can create a binary search algorithm using low, high in a while loop condition, and then constantly update mid by grabbing low plus the half distance, which half distance can be represented as high minus low divided by 2. After that, we have 2 if conditions. So this one, I'm going to go ahead and simplify this. So if not within contract, and we're measuring that mid distance as k, we actually want to increase low. That means the stage size was too small to fit that contract time limit. So we increase the stage size to reduce time on stage and be within contract time limit. We constantly do this until we converge at a point where within the contract time limit between a false and a true. So that means after our binary search is done, we can go ahead and write the smallest possible stage size k. And that convergence value is going to be high. So the last recorded k value that was within contract limit. Then we could go ahead and close our output file. Now the hard part is actually creating this within contract method. So we're going to go ahead and create that here. So we're going to say private static. We're returning a Boolean. We're naming it within contract. And our input is going to be int k. Now, earlier I said there's 2 ways to do this. There's one where we search for a minimum dance time and our stage array, and then subtract it across all our values. That's very inefficient. Instead, we can use a priority queue and pop the minimum dance, then push a new value where it's the minimum dance value plus the next cow dance time in the dances array. That is a lot more efficient than changing every single value on each iteration. So let's start off with priority queue, and you'll see why I used a list data type. We can go ahead and quickly build the heap in O of n time by just feeding stage with a dances subarray or sublist from 0 through k. After we created our priority queue, we can go ahead and apply this push and pop approach. So we elapse shortest dance time by using poll to open dance spot and add next cow to stage. We're essentially pushing hold value plus next cow dance time. And what that's going to look like is we iterate through the dances or list starting from k and continuing on until n. Then we solve what is the minimum dance in the current priority queue by grabbing the root and popping it at the same time, then pushing, or in this case we just say add, that minimum dance time plus the current index element we're looking at. After this, we'll see that we can elapse remaining time by returning the max dance value that has been increasingly summed up to throughout the for loop. However, there isn't a built-in max function for priority queues. So what we have to do is create another value here in Java where it's int max dance is equal to integer.min value. So now that we've initialized this, we can go ahead and constantly update this value here with its previous value and the new value that's going to be pushed or added into the priority queue. Then we can create this return statement where we're comparing max dance to tmax and tell us if we're within the contract time limit of Tmax. So now I'm going to go ahead and run this. We got 4. Great, it worked out for us. Now I want to talk about the time and memory complexity. Now we used a binary search approach, which takes log n time. We also used a for loop of all of n time, so n plus log n so far. However, inside of our binary search problem, we have a for loop of n time, and we have procedures that are happening at log n time with add and pull. So therefore, that time complexity is n times log n. And that memory complexity is O of n, where we have the size of stages. That completes the solution of the problem. And now we're going to go ahead and try to submit this on the website. So now that we're here on the website, we're going to go ahead and choose Java, then choose the file. Now we submit solution.java. Now that concludes our solution for Java. Thank you.